This is the first session of the optimization lecture, and we'll start out by considering what do we mean by a global optimum. And by this, let's assume that we have some set, and here I've got the set as this D. I'll outline a little bit of it here. I miss it somewhat, but there's my overall set of objects, and I have a function that maps that set to the real line. And I want to know, is there a subset of D that give the largest value in R? And that would be some subset, let's say for example D star, in which all of the points in D star map over to a particular value that is the largest. Any other point that is not in D star will map over to a value that's less than those in D star. From this perspective, then we would have a global optimum. And it would be the set, D star, that gives you that global optimum. Notice that there can be more than one point that can give you an optimum. If D star has only one point in it, then it is a unique global optimum. All right. That's essentially what I'm saying here. This is essentially a notation that is not what we're going to use for most of the time, which would be some sort of an absolute value or determinant in most of our math for the semester. But for the moment, what that is considered the cardinality of the set D star, and really just means how many elements are in it. And if there is a single element in it, then we have a unique solution. Notice also the terminology here that if there is a particular point A that provides the maximum under F, then we can write that as argmax. What that means is it's the argument of the function f in the set D that gives you a maximum. An argument also can be noted that when you have a function of some set of values, this is considered the argument in this language. Okay. Now, finding a minimum would be the same concept, right? We're looking for now the values that minimize a function. And what are the values in the domain that provide the lowest value of the range of the function? And that would be a minimum. And you would write that as argmin f in terms of just the language. Now, this is a global, and that means across the whole set, we are identifying those values that maximize the function. What will be of great interest to us will be unique maximum and local maximum. By local, what we're considering is there may be points in the set D that have a larger value, but the points around a particular point you're looking at would be either all smaller than the given point, which would make it a local maximum, or all larger than, which would make it a local minimum. And in order to do this, we actually have to define the set we're looking at in a much more rigorous way. It would be, for example, a metric set. In other words, we could tell distances around it. The points are organized in a particular fashion. So, for example, let's say that our set we're looking at is the bottom here. Maybe these are a set of values of x, and our y-axis are the values of the function with respect to x. Notice that here we have the two largest points. They are actually the same, right? They come right across to the same value of y, you could think of it as. And being the same, we have a set of 2 points, which is this x1 and x2, that give you the maximum of the function f. And it's a global maximum because there is no other value of f, at least within the range that of x's that we're looking at here, no other value that makes it larger than that. Okay? But also notice that if we were to just look closely right here, so we take a magnifying glass here, we look right there, we would notice that there is a point x3, around which there's a neighborhood then of values in here around x3 in which they're all less than, right? The functional values are less than. So this here is a local maximum, and x3 is the value that provides the local maximum of fx. Here's another local maximum, and here's another local maximum, and perhaps this one is here. I say perhaps, depends on what this is doing. If this is keep going down, then that would be the local maximum. Now similarly, we would notice that there is a point here, x4, and that is a global minimum. And let me make this pen a little bit thicker than the thin one. Okay. And here we have some local minimum, all in here. Okay, so the global max and min have to do with the full range under consideration, or the full domain of the function f. And local are just about neighborhoods around points. Okay. Now this is going to be very important because we're going to do a lot of our identifying optimum points by really just identifying local optimum points. And this will also be a reason for being cautious with the kind of results that we get. Because we may settle down right here and say, aha, I've got an optimum, and what we don't know, if we're looking too closely here, is that there is another value that actually is higher. So we would pick this particular x when in fact it's this x that is best. Also notice, here's another function, that you can have a whole range of values again. There's a whole range from x1 to x2, all of which give the maximum of the set. So when we compare, here is an example of a unique optimum. This is an example where it is not unique. There's a whole set of values that give the maximum point. And what does a unique optimum mean? It means there's exactly one point in x, a specific one, that gives the maximum. You move away from this point no matter how small of a move, and you will be at some value lower than the point at xi. Xi provides a unique maximum. Similarly, if this were xj and xj provide a unique minimum, it's because, at least a local minimum, then any point as you move in some small neighborhood around j will give you a higher value of the function. So this is a unique minimum. This provides a unique maximum. Now let's consider optimization in terms of some concepts of calculus. What do we know about, from just kind of our basic calculus definition of a maximum? Well, with a continuous function and a unique maximum, then we have, if we're standing at the top of the hill here, the slope must be 0. Notice that the slope is not 0 as you move away from that point, right? If we were over here, it's not 0. Over here, it's not 0. It is 0 right at the maximum. So that is to say that the derivative of f with respect to x is equal to 0 at the maximum. What is happening to these slopes? Well, here is a positive slope, and as I move from this point of x and move this way, the slope gets less and less, goes to 0, and then it becomes negative and more negative and more negative. So the change in the slope is negative. So at a maximum of a continuous function, where the maximum is an interior point. Interior means that it is on the inside of the boundaries of the domain. You have a maximum if, a local maximum at least, if the derivative is 0 and if the second derivative is less than 0. Similarly, if you are at a minimum, again, your slope is equal to 0. But now the slope is changing. Here we've got negative, less negative, less negative, 0, positive, positive. And so the change in slope is positive. Maximum and minimum each have the same characteristic with regard to slope, and that is that they're both equal to 0. But the maximum has a second derivative that's negative, and the minimum has a second derivative that's positive. So now, let me ask this again. I've given you some sort of a suggestion already. Is it the case in general that the slope is 0? Is this always the case at a maximum? And here I did not qualify it with my statement of an interior point, and that's going to be the key, right? So for example, if this was our range going from here, x1 to x2, and this were our function, our maximum would be at x1, and the slope would not be 0, but it's on the boundary. It is on the boundary and not an interior point. So this case of the derivative equal to 0 is really an indicator of a maximum or a minimum of an interior point, not on the boundary of the domain of the function. Now what about this case? Is the second derivative always less than 0 for a maximum or greater than 0 for a minimum? Well, it kind of depends on how you want to look at this. What is this case here? Here's an example. Actually, not only is it a boundary condition, that's what I'm showing up here. Let me go back to this derivative here. But also in discontinuous functions, such as this one here, where the two slopes are basically coming up against each other and it does not round over. This would also not have a 0 derivative at the top. This is not to be confused with if I were to blow this up with some sort of a curvature. There is not. That's not what we're talking about. We are talking about no matter how much you blow it up, it is like this. And if you blow that up, you get like this. So that there is no actual 0 slope. This would be another case. This would actually be an interior point. But the function itself is not a classic continuous function with the smooth derivatives that we normally think of for interior points. But we could come up with something like this that would be an additional condition where the slope is not equal to 0 than simply the boundary conditions, as I showed up here. And here we go again with our boundary condition. Now what about the multivariate case? And this is where we have more than one dimension. You could think of it as standing on top of a hill if you're at the maximum, or standing in the bottom of a valley if you're in the minimum. How do we know whether we are at the top of a hill or in the bottom of a valley? Well, if you're standing at the top of the hill, no matter which way you look, whether you're looking this way, that way, no matter which way you look, or no matter which way you step, you would step down, right? And in terms of a minimum, no matter which way you look or go, you would step up. That would mean that you're at a minimum. Another way to think of that here is our point in a two-dimensional space. We're looking down on it like a topographical map, and as this arrow swings all the way around, as you're looking at it from different directions, if it's a maximum, the function is always going down in that direction. If for some reason you're going up, then you wouldn't be actually at a maximum, since you could take a step and you could get higher. Right? Same thing would apply down here in the minimum in terms of if this were a minimum going down, and no matter where you looked at, it was going up, that would be a minimum. In this case, we're writing this as beta being a single point and a unique minimum. If this whole area up here was a flat plateau, then this concept of going down would not apply in the interior part of that set. It would only apply in the directions away from the interior along the edge, but that's a little more complicated geography in thinking about this. Typically we're thinking about unique points, and so really we're just going to talk about a single point as a unique optimum. So what are we saying? Well, it is a maximum where the slope at beta star is equal to 0 for all directions. No matter which direction that you are kind of pointing, the slope is 0. Another way to think of it is that the tangent to this hilltop, at the very top, if you were to lay a tangent plane at the top, it would be flat in all directions. So at beta star, in all directions, the slope is 0. Also, it's the case that if you were to step off from that point in any direction, then the value of that point beta that you stepped off from is going to be lower than the value of beta star. In other words, f at some other point beta less than f at beta star, which is our maximum, that distance is going to be less than 0. I'm going to step down, basically is what it says. Minimum is just a little bit different. Minimum has the same idea that it is flat at that point. If we have some, not a very good drawing here, some three-dimensional bowl, and if we took a tangent plane at the bottom point, it would be flat. This whole surface would be have a 0 slope in any direction. But in this case, if I take a step to any beta that's nearby in any direction, the function f is going to be larger than the function at beta star, so this difference is going to be greater than 0. So basically I'm saying that if I'm at a minimum, obviously I'm stepping up in any direction that I go. If I'm at a maximum, I am stepping down in any direction that I go. Now this is key, this idea of f at beta minus f at beta star being greater than or less than 0. We can see this in a mathematically pragmatic way by considering the Taylor series approximation of f around beta star. So f at any beta is equal to f at beta star plus the gradient at beta star times the distance between beta and beta star. And my second order term is going to be the 1/2. Doesn't really matter, but it's 1/2. You've got your vector of beta transpose the second derivatives at beta star, and the beta minus beta star, or the step that you took, and then plus a residual of higher order terms. So as an approximation, when you get beta getting really close to beta star, so the higher order terms just become trivial, we can look at f beta minus beta star is approximately 1/2 of the beta minus beta star distance transpose times the second derivative matrix times the beta minus beta star. As we said before, that would need to be less than 0 if it's a maximum and greater than 0 if it's a minimum. Well, what does this mean? This is a matrix. The second derivative here is a matrix right here. That is a matrix. This is a vector x, and we have it squared essentially, x transposed mx. We call this an x as a vector, and this is my matrix M, and this is x. Look at x transposed mx is less than 0 for all points beta near beta star, except for where it's equal to beta star. and we have our definition of a negative definite matrix. So beta star is a maximum if the matrix of second derivatives is negative definite. It is a minimum if the matrix of second derivatives is positive definite. So this is a important point because we will use this in our various optimization search techniques, as well as our ability to evaluate whether we are at the maximum or the minimum of some service. So, how then do we find an optimum? Well, depending on the function, we might just solve for it, right? We might use our techniques from economics and comparative statics. We might solve the first order and second order conditions. First order to be able to get an optimal point, second order condition to find if it's a maximum or minimum. We may solve for them statistically in a simple solution, such as ordinary least squares. But there are occasions in which, in any case, that we can solve for our optimum points. Or we can search for them. In other words, we can use an algorithm that will generate a sequence of points, beta 1, beta 2, beta 3, such that the sequence of points converges to the actual optimum. Or we can do kind of a exhaustive search, meaning that we evaluate all the points in the space. This is going to be problematic if there's a lot of points or if it's a continuous set. If not, then maybe what we do is we lay a grid across the space of possible points, and we search out the points in the grid, and then we might refine it around the largest point and do a smaller section with more grid points. We might use something called a simplex, which I won't discuss here, but it's another method. It's actually a kind of algorithm this way up here. We might randomly search. Now, you might think that that's kind of an odd thing, that we just simply randomly pick a point, see its value, randomly pick another point, see if it's larger. But actually, this is a very useful strategy for highly complex sorts of equations. There's two ways of doing this that are very common. One is called simulated annealing, another one called genetic programming, depending on the kind of space that you're trying to search for an optimum. The advantage of these is that they actually find global optimums. Unfortunately, they're only guaranteed to do so in infinite time. It's kind of like our statistics when we talk about infinite sample sizes. Well, in this case, it's in infinite time. Simulated annealing genetic programming will find the global optimum, not just local optimum. But they can be useful. I have used them before in nonlinear neural networks, and they actually can do a reasonable job. I won't get into details here because for what we're doing in this class, we're not going to be using either one of those. Although we will get somewhat close to this in a Metropolis Hastings sort of strategy. Not exactly simulated annealing, but sort of has that flavor to it. Or perhaps we just simply, wherever we're standing on our hill, we just go in the direction that gets closer to beta star. That would require that we know where beta star is. Or maybe we just go in the direction that's going uphill, which may not be getting us towards beta star, but it seems like a reasonable thing. If I'm standing on the side of a hill and I want to get to the top, maybe I should go uphill. So this is one way. We'll talk about this in a little bit greater detail at the moment. The method of steepest ascent. And this is also one of those algorithms that gives you a sequence of beta i's. So what we're doing is we are going to find the next step, the next point, as a point beta I that will maximize our function such that my step is a certain length, specifically given that my step distance here squared is k, my actual step length is the square root of k. Now to look at this, we'll look at the Taylor series, first order Taylor series approximation to see what we get. our first order Taylor series approximation, is to say that I am going to look at the function at beta I, my next step, around my current function at beta I minus 1. And a first order Taylor series is going to say that beta I is equal to the function value at beta I minus 1 plus the difference between beta I minus 1 times the derivative of the function at beta I minus 1. I'm standing right now at beta I minus 1. I'm trying to figure out where to go next. Well, I want to find the beta I that maximizes this function subject to this particular step length. I just decided I just want to take one step, and my step might give me a 1.5 foot step. So given that I'm going to take a 1.5 foot step, where should I go? I want to go to that point that will give me the largest value of my function, will be the highest point on the mountain, given that I'm only going to be moving essentially the square root of k distance. So we set up a Lagrange function. We take the derivative of that function with respect to beta I. And if we solve it, we will find that my next point, beta I, is my current point plus some scale factor times the derivative, which is the slope at beta I minus 1. Now here I'm just going to call this scale factor delta. And what I have is my beta I is the new point, is going to be the point where I was at, some what's called step length times essentially the gradient. So I'm going to move along the gradient, or I'm going to go along the direction of steepest descent. If I was going to minimize, it would be similar, only now I'm going to go along the direction of the steepest descent. So it's a very simple algorithm. I'm just stepping in a particular direction or a particular step length or a scale factor of delta according to the derivative, steepest ascent. Okay, now let's look at some consequences. This black curve is my function. And notice what it means as my point, beta, gets closer to the actual value, beta star. The slope is getting shallower, right? So that's an interesting point. We are saying that the closer that I get to beta star, the shallower the slope. Let's reverse that and say if I'm facing a steep slope, maybe I can step a longer distance. And if I'm facing a shallow slope, then maybe I can step a shorter distance. What about the curvature? Curvature would be similar, and only just the opposite. Similar, but the opposite. It goes this way. If beta 1 star was the optimum, and I'm at beta I, the curvature is a lot steeper curvature. If instead the optimum is at beta 2, and I'm at beta I, the curvature is less steep. So what do we say? Basically, that if I were to consider my step distance to be proportional to the slope, the steeper it is, then the further away I am, and inversely proportional to the curvature, the greater curvature that I have, the closer I am, then we might consider setting up a simple little algorithm that says I will take and find my next beta I as where I'm currently standing, a particular step distance, and it will be in association with, it'll be a further step if the slope is larger, and a smaller step if the curvature is larger. This will be a You can think of this as kind of one step more complex than steepest ascent. Steepest ascent, if you'll notice right here, is just simply using this portion, right, where it was beta I is equal to beta I minus 1, some step distance times the slope. Well, now if we divide it by the curvature, we will have a slightly different algorithm to go to our next beta I. And it will turn out that this kind of a structure here is going to show up in most of the more efficient algorithms for finding optimums. So this is the end of session 1 for the optimization lecture. And you can go to the next session 2 to continue.